Today we are going to talk about transformers, and we're actually going to talk about transformers. So this will be Transformers Lecture 2. I am very creatively calling Transformers 2. And so we are going to consider a transformer to be a magnetically coupled circuit consisting of two or more windings and our windings are what we've been calling coils to this point, coupled by a common magnetic circuit. And I'll give you two quick examples of transformers that you might see out in the wild, so to speak. So this first type of transformer we've looked at a couple of times. This is what's called a core type transformer. So we'll have some winding wrapped around one leg, like so. I'm going to call this coil 1. So it has N1 turns and is going to be carrying a current I1 of T. And over here, this will be coil 2. This one will have N2 turns and will carry a current I2 of T. And then over here on the right, I'm going to put a shell type transformer. Like so. And in a shell type transformer, we typically wind up wrapping both of our coils around the same structure, and it's usually the center structure. So this will be coil 1 carrying current in this direction with N1 turns. Over here we'll have our second coil, like so, carrying current I2 and having N2 turns. Said this is a shell type transformer. Can anybody think of a reason why we might prefer a shell type transformer over a core type transformer? Possibly. So that could be a thing. So we have the reluctance of the center branch and then those two branches in parallel, and because they're in parallel, they're going to look small. So that's fair. But usually it's done because of the mechanical strength of a shell type structure versus a core type structure. So it's more rigid and so it's less likely to be damaged if something happens. All right, so I have drawn the coils in such a way so that our flux generated by I1 is in this direction, and our flux generated by I2 is in this direction. And this guy, both of our fluxes are in the same direction as well. And I know that when I taught you guys in your ELET 280 class and all that kind of stuff, we talked about coil polarities and this, that, and the other, and using the dot convention. In this class, we're always going to assume that we're going to have positive dots on the same side, so I'm not going to ever bother drawing them. So effectively, unless we're explicitly told otherwise, all of our windings are going to be situated in such a way that the flux that's generated by coil 1 passes through the positive polarity terminal of coil 2, and any flux generated by coil 2 will pass into the negative polarity terminal of coil 1, so that the math works out nice and pretty effectively, so that we don't have to get into the headache of the dot convention and paying attention to the signs of the mutual inductances and all of that kind of good stuff when we're going to look at transformers. All right, so our schematic representation of a transformer is as follows. So in a diagram, we would simply represent a transformer by pair of coils. Like so. A couple of variations on this thing we might see. So we may be told the number of turns for the coil on the left-hand side. We may alternatively be told the inductance of the coil on the left-hand side. Be told the number of turns for the coil on the right-hand side, or the inductance for the coil on the right-hand side. We may also see vertical lines between our coils. These vertical lines are typically indicative of us dealing with an ideal transformer, and they represent that our coils are very tightly coupled together, or really it's perfect coupling, and all that kind of good stuff. So just letting you guys know the different variations that you might see. Typically, one winding is connected to an AC supply, and the other is connected to an electrical load. The winding that is connected to the AC supply is commonly referred to as the primary winding. So I'm going to put that down over here. Primary winding. Connected to the source side of a circuit. And the secondary winding is usually connected to the load side of a circuit. When the number of turns in each coil are not equal to each other, so if N1 is not equal to N2, then we also have some other common terminology that we use. So whichever coil has the larger number of turns is usually referred to as the high voltage or HV side of the transformer. And then whichever coil has the smaller number of turns is the low voltage or LV side of the transformer. And here in a couple of minutes, we'll figure that, or why that nomenclature is used if we don't remember exactly how ideal transformers work from our previous classes. All right, so transformers are used in a variety of applications. Some of the applications that you guys may see or may have seen already in your internship experience and stuff like that would be using a transformer as an isolation transformer. So isolation transformers are used in low power electronic and control systems to isolate circuits and enable impedance matching for maximum power transfer. So we might have a situation like this. So here is our AC signal source. And we're going to treat that signal source as if it were a practical voltage source. That signal might be applied across the input terminals of a amplifier. Where this resistance here, R sub N, is the input resistance of the amplifier. And this will be the input voltage of the amplifier, Vn. Over here, we're going to have the output side of our amplifier. So this is going to be some transconductance gain Ag multiplied by Vn. That's going to be in parallel with the output resistance of our amplifier. And then over here, even further to the right, we might finally have our transformer. Let's assume an ideal transformer. And then this will be our primary, this will be our secondary, and the secondary of the transformer might be connected to some type of load impedance, R sub L, like so. Let me denote this really quickly. This is the output voltage of our amplifier. Not that it's particularly important to this class, but I'm going to break this up into stages so we can kind of talk about what this thing represents. Because this diagram here represents a whole hell of a lot of circuits that you might see in a variety of applications. So over here on the left-hand side, we have our source. Here in the middle, we have our amplifier stage. Over here, we have our transformer. And then over here, we have our load. So can anybody think of a system that might be described by this generic circuit? Anybody here play electric guitar like I do? At least one of you? So the source in this case would actually be your guitar. You plug it into your amplifier, and then the amplifier provides some amount of voltage gain. Then you need a transformer to be able to match the impedance of your speaker cabinet to the output resistance of your amplifier. So typically speaking, for a tube amp or something like that, output resistance of the power amplifier stage is usually on the order of kiloohms. Matthew, since you play guitar, do you have any speaker cabinets or anything like that? I have a combo. Okay, so you have a combo amp, so all of it's done for you. So typically speaking, the impedance of a loudspeaker is usually either 4 ohms, 8 ohms, or 16 ohms. And so what this transformer is used to do is to make this 4, 8, or 16 ohm impedance from our speaker look like 10 kiloohms or something, whatever this output resistance is, so that the maximum amount of power is delivered to the load so that you don't cause damage to your amplifier and all kind of stuff like that. So very, very practical application for the use of an isolation transformer in this bed. See it literally all the time. We have stuff like this in every one of our vehicles and all that kind of good stuff, which allows us to listen to the radio and all of our podcasts or whatever the hell it is we're listening to nowadays, all that kind of good stuff. Okay. Instrument transformers is another application. So instrument transformers are used to measure voltages and currents in an AC system. So how many of you guys have had an internship before? Few of you. Where did you work, Bailey? Royal Martin. Okay, so that was a paper mill effectively, right? Or wood processing. Preston, where did you work? CF Industries. What do they do? Okay, so the chemical plant probably gonna, did you guys work with what are called CTs or VTs at all? Yeah, so CTs are current transformers and VTs are voltage transformers. They are literally instrument transformers designed specifically for measuring voltages and currents as part of a control system. So for those of you that go into manufacturing industries, you're going to be dealing with instrumentation transformers or instrument transformers constantly. That's going to be a huge part of how you're going to set up automated systems in order to do anything. Okay. For those of you that go into the utility industry, working for electric companies like Entergy, AEP, SWEPCO, Pleco, things like that, you might be dealing with power and distribution transformers. And these are used specifically to step up or down voltages in the electric utility industry. I put too many T's in utility. So, yeah, I think there's enough space to do it here. So we might have a situation like this. So over here on the left, we might have some AC generator. So this could represent coal-fired power plant, a hydroelectric plant, a nuclear plant, or something like that, where you're effectively just wind up pushing steam through a turbine to generate electricity. And we might see that the voltage present at the output of that electricity generation might be somewhere in the ballpark of 30 kilovolts RMS. That 30 kilovolt RMS voltage would be fed into a power transformer, which would step it up to somewhere in the ballpark of 500 kilovolts RMS. Around here, I think our largest distribution voltage, I'm remembering correctly, is 197 kV. And that's the voltages on the lines that you see when you're heading out towards Mississippi. So after Monroe out towards Mississippi, I believe those are 197 kV lines, but I might be misremembering. Then when you get closer to a city, you might see a substation where that voltage gets stepped back down to a more acceptable level, something on the order of 44 kilovolts or so. Then as you get closer to a neighborhood, it'll be stepped down again to something like 4.6 kV. Around here, I think we actually use 13.5 kilovolts. And then finally, that voltage is stepped down one last time to the 120 volts that we use at our house. So just for illustration purposes, everything to the left over here is what's considered generation. Everything between here and here, so where the 30 kilovolts is getting stepped up to 500 kilovolts, and actually all the way to this point, my apologies, where it's getting stepped back down, is what's called transmission. And then everything from this point where that really high voltage is stepped down all the way to where it's the voltage that we use at home, is distribution. So if you ever talk to a power engineer, distribution, that works for a company like Entergy, AEP, or anything like that, they're going to tell you they work in one of three divisions: generation, transmission, or distribution. And that effectively tells you what size of voltages they're used to having to deal with and what their design focus is. The only difference between distribution transformers, which let me just identify things here. So this would be a power transformer. This is a power transformer. This is a distribution transformer. Actually, this one might also be a power transformer. And then the distribution transformer is what they're rated to do and therefore what insulation levels they have. So physically, they're pretty much the same damn thing. It's a pair of coils wrapped around something with some particular turns ratio. But then you have to use different size conductors and all of that kind of stuff to safely handle the large voltages and currents seen at the various steps. All right, so these are the main applications that you guys will deal with throughout your careers, internships, and all of that kind of stuff. So now let's get down to the nitty-gritty of figuring out how these things work. And so this part should hopefully be a bit of review from what we covered in 280 last spring. So let's talk briefly about ideal transformers. Okay. So I'm going to draw a simple circuit here. So I've got some input voltage V of t. And this pair of terminals here are the terminals of my transformer. And then over here, I'm going to draw a simple magnetic circuit. like so. So that's my core, and I'm just going to wrap a wire around this guy. This is going to be my current I1 of T. This is my voltage V1 of T. And here, I'm going to have my voltage lowercase, sorry, E1 of T. And so I want to talk about the distinction here. So whenever I'm going to use the letter E, pretty much from here on out, that's me saying that we're dealing with an induced voltage, okay? So that's the voltage drop that's induced across the coil due to some amount of flux flowing through that coil. The voltage that we have over on the left-hand side, V1, is what we're going to consider to be the terminal voltages of our transformer. So the terminal voltages are something that we can measure with an instrument, and the induced EMF, E1 and E2 on the secondary side, are something that's going to happen over the coil that we can't really see, but we know that it's happening. In the case of an ideal transformer, and I'll write this part down in a moment, we are making an assumption that our winding or our coil has no inherent resistance of its own. And so that's going to make our terminal voltage and our induced voltage the exact same thing. Here in about half an hour, when we start looking at practical models for transformers, those two quantities are no longer going to be the same thing. So I'm just trying to help you guys sort out the nomenclature here. So this coil will have N1 turns. And then over here on the right-hand side, I will have a second coil. Give myself a set of terminals. Wrapped around this way. So this is going to be my terminal voltage, V2. Here explicitly, right next to the coil, I'll have my induced voltage. I don't know why that's not drawing a parentheses well. There we go. E2. That E2 looks shitty. E2 of T. There we go. And then if I have any current flowing in my secondary, that'll be I2 of T. And then over here, I'm going to put a switch. And then some load impedance, ZL, like so. So the transformer can be considered ideal if it has the following properties. So number one, the resistance of the windings are negligible. So this effectively means that no appreciable voltage drop occurs across the wire of the coil, so that any voltage that we are going to have is the induced voltage. So this means a couple of different things. One, we're not going to have any losses due to heat from our windings heating up or anything like that when we pass current through it, which we would represent with a resistance. Since we don't have that resistance, we therefore don't have a voltage drop. And so our terminal voltage V1 and our induced voltage E1 will be the same thing. On the secondary side, our terminal voltage V2 and our induced voltage E2 will also be the same thing. Okay? So that's one assumption that we're making. Our second assumption is that all fluxes are confined to the core and link both windings. So we are in this statement saying effectively that we don't have any core losses to worry about, so that we're not really saying we're losing any energy to magnetizing or demagnetizing our core or anything like that. And then our third assumption is that the permeability of the core is infinite, meaning mu c is approaching infinity. So this tells us that it takes practically no current whatsoever to generate an EMF sufficient, excuse me, to generate an MMF sufficient to drive flux around our core. Another way to think about this is that our reluctance is effectively zero. So under these three conditions, we have an ideal transformer. Okay. All right, so now let's look at this circuit. Okay. So with our switch open on the right-hand side, let's say that we were to have some time varying voltage V1 applied to our circuit. That voltage V1 is connected to the primary windings, and it will establish a time varying flux phi of t in the core. So we're going to have some time varying flux. I'm going to call this phi 1 of t because it's caused by the primary windings circulating around our core like so. Because we have a time varying flux passing through our coils, a voltage E1 will be induced in the primary winding such that E1 of t is equal to N1 times the derivative of flux 1 with respect to time. And because we have an ideal transformer, we can say that this is equal to V1 of t. So now I'm just going to do a very small amount of algebra. I'm just going to move that factor of N1 from the middle underneath the voltage V1 so that I can see V1 of t divided by N1 is equal to the derivative of phi 1 with respect to time. So all of our flux, phi 1, passes through coil 2 as well, right? Because coil 2 is open circuited, at this exact moment, we're not going to see any current, but we should see some voltage drop induced across our coil, right? So the induced voltage drop across our second coil will be E2, and that's going to be N2 times the derivative of the flux, which is just phi 1 with respect to time. And because we're dealing with an ideal transformer, E2 is equal to V2. We can rearrange this relationship to find that V2 over N2 is equal to the derivative of our flux with respect to time. And now we have two different quantities that are equal to the derivative of our flux with respect to time, so we can set those two things equal to each other, right? So if we say that V1 of t divided by N1 is equal to V2 of t divided by N2, this relationship can be rearranged such that we see V2 divided by V1 is equal to N2 over N1, and we're going to call this A. Our turns ratio. So we can manipulate this a little bit here. I'm going to do this in blue because this is kind of an aside thing. So we can see that V1 is V2 over A, or alternatively, we can see that V2 is V1 times A. Actually, I'm going to move the A to the other side. So A V1 of T. So if N2 is greater than N1, then that means the quantity A is a number that's greater than 1. So we would have what's called a step-up transformer in this case, because the voltage in our secondary windings is going to be greater than the voltage in our primary windings. If N1 is greater than N2, the quantity A is a number that's less than 1, right? So we would have a step-down transformer because the voltage drop across our secondary windings is lower than the voltage drop across our primary windings. Okay? So the turns ratio tells us a whole heck of a lot. Is there anything that's forcing us, if we're putting a transformer in a circuit, is there anything specifically that forces us to connect one coil to the high voltage side and the other coil to the other side or anything? Not at all. Like a transformer is completely and utterly interchangeable. So it's up to us to connect things correctly to get the desired response. Do we want to step the voltage up or not? Kind of thing. All right. So now let's close the switch. So with our switch closed, we should see some current, I2. Based on the direction of our winding and the direction of our current I2, what direction is our flux generated by I2 going to be? So okay. So our flux generated by our second coil, let me do it in a slightly different color, is going to be passing around the circuit also in this same direction, right? Based on the direction of our current as well as the direction of our winding. So it's going to induce a counter MMF in coil 1, because Lenz's law says that I don't want the flux to change. So effectively what we're going to see is that there will be a net MMF in our system and it will be N1 times I1 of t minus N2 times I2 of t. So these are of opposite signs because we know that Lenz's law tells us that this change is going to cause our other coil to act in opposition to the change. Okay. And this net MMF must be equal to 0. So from this, we can see that N1 times I1 will be equal to N2 times I2. And this relationship can be rearranged such that we have I1 of t divided by I2 of t is equal to N2 divided by N1, which is once again our turns ratio. I want you to notice things here, though, very explicitly. When we did this for our voltage to define our turns ratio, the secondary voltage was in the numerator and the primary voltage was in the denominator. Here with the currents, our primary current is in the numerator and our secondary current is in the denominator. So these are switched. So effectively, what we'll see is that I1 is equal to A times I2, or alternatively, I2 is equal to I1 divided by. So now, let's look briefly here at power. So my current I1 is flowing into the positive polarity terminal of my induced voltage E1, right? So that coil is absorbing power from my excitation source over on the left-hand side, okay? So the amount of power that I'm absorbing is V1 times I1. My current I2 is leaving the positive polarity terminal of the induced voltage E2. So that means that V2 times I2 is the power that's supplied by coil 2. Another way we could think about it is that's the amount of power that's absorbed by our load, the output, right? What's the relationship between these two powers? They're equal. So if we have an ideal transformer, the power that we absorb at the input has to be the power that's supplied at the output, and vice versa, because we've explicitly got a circuit where there are no losses, right? So P1 will be equal to V1 times I1, which will be equal to V2 times I2, which is equal to P2 like so. So what does this tell us? Well, if we have a step-up voltage transformer, the current has to be stepped down in order for the power to remain a constant quantity. Similarly, if we have a step-up current transformer for whatever reason, the voltage has to be stepped down in order to keep powers a constant quantity, right? So we're not generating energy out of thin air by stepping up voltages, stepping down voltages, stepping up currents, or stepping down currents. All of this is rooted in a physical principle that says energy in has to equal the energy out, and therefore everything has to change to accommodate any other change that we introduce by stepping up or stepping down voltages and currents. Okay. All right, so let's talk very quickly about impedance transformation. So let's say that I have the following ideal transformer circuit. So I have some excitation source, doesn't matter if it's a voltage or current source. And my terminal voltages for the primary side of my transformer is going to be an RMS voltage V1. And my primary winding should carry an RMS current of I1 like so. Over here on the secondary side, I'm going to see that a current I2 is flowing out of the winding. I'll have a terminal voltage of V2. And I am supplying power to some arbitrary load, ZL, like so. So by definition, my impedance Z2 is going to be the ratio of the voltage drop V2 over the current I2. The impedance seen looking into the primary windings, I'm going to draw an arrow here. Actually, yeah, that'll be fine. So the impedance seen looking into my primary windings, Zn, is going to be the ratio of the voltage V1 divided by the current I1. Since we have an ideal transformer, we know that the voltage V1 and the voltage V2 are related to each other through the turns ratio. And we also know that our current I1 is related to our current I2 through our turns ratio. So how am I going to express that voltage V1 in terms of V2? Literally wrote it down up here for you guys' benefit. So V1 is equal to V2 over A. Up here, we expressly derived it for a time varying voltage. Down below, we're doing it specifically for a sinusoidally varying voltage that we're representing with RMS voltages and currents, but the same exact relationship, right? Nothing should change whatsoever. So we're going to have V2 over our turns ratio A. And then how am I going to express I1 in terms of my current I2? I2 times A, okay? So I'll put A times I2 like so. So this is going to look like V2 divided by I2 multiplied by 1 over A squared, right? Because I have a 1 over A in the numerator, and then I already have an A in the denominator. Those guys get multiplied by each other, and it looks like 1 over A squared. So V2 over I2 is nothing more than my impedance Z2. So this looks like Z2 over A squared. And we're going to call this, sorry, I've been using Z2 here. Realistically, this should have been ZL, so I'm going to just fix that before I confuse everyone. We're going to call this ZL prime. So this is our load impedance referred or reflected to the primary windings. So that realistically, we don't actually need to analyze the circuit with a transformer in it at all. If we know what the impedance looks like, we could just move it over to the primary, and then we have our excitation voltage source, this new impedance, that's the reflected version, and then we could do any circuit analysis that we so chose to do. If we ever needed to reflect an impedance from the primary side to the secondary, what do you think we would do? So to go from the secondary side to the primary side, we divided by A squared. So to go from the primary to the secondary, we should multiply by A squared. That's simple. So let's take a crack at in-class assignment problem 1. I did not have an opportunity to get the answers and all of that kind of good stuff. So that's why we're working it together, so we can see how things shake out. All right, so in this first problem, we are told that we have an ideal 44 kilovolt RMS / 220 volt RMS power transformer. Is rated at 240 kilovolt amperes. And is used to step down a 60 hertz voltage in a distributed system. I think that's probably supposed to be distribution system. I want us to determine the following quantities. So part A, the magnitude of our rated primary current. Part B, the magnitude of our rated secondary current. Part C, the load impedance seen between the primary terminals, ZL prime. So this is our reflected load impedance under the constraint that the transformer is fully loaded and the load operates at a power factor of 0.90 flag. So Bailey, I'm going to do you a solid. I'm going to draw a picture. So over here, we have our excitation source, whatever it may be. And we have our ideal transformer. And then over here, we have our load impedance. Okay. So this is going to be my voltage V1, my current I1, my current I2, and my voltage V2. All right, so a couple of things that we potentially need to discuss here. It's based regarding the terminology that we're using. So what does it mean that our transformer is rated at 240 kilovolt amperes? It's the maximum apparent power that our transformer is capable of handling, right? So I can say definitively that we're talking about apparent power because the units are expressed in kilovolt amperes. Anybody remember what the relationship for apparent power is? So complex is the real and the imaginary put together. So let's do a very, very quick review of complex power relationships. Just super quick here, because it's been 6 months or so since you guys have had to deal with any of this, right? So complex power S is by definition the product of our phasor voltage multiplied by the complex conjugate of our phasor current. It can be expressed in rectangular form as average power plus reactive power. So let me write this down. This is average power measured in watts. This is reactive power measured in VARs. And it can also be expressed in polar form as the magnitude of S with an angle of theta S, where this magnitude of S is what's called the apparent power, measured in volt amperes, and theta S is our power factor angle, usually measured in volts because it's an angle. Just as the quick aside here on the right-hand side, I can say that S is V times I conjugate. P is V times I conjugate times the cosine theta S. Q is V times I conjugate times the sine of theta S. And the magnitude of S is just V times I with no conjugate. So these are all of our relationships. And again, I encouraged all of you, I believe, to buy calculators that can do this math very easily so that you can just let your calculator handle all of this other stuff. Showing you the other relationships in case we need them. So circling back around, we know that our apparent power is 240 kilovolts. So we can use our apparent power in order to determine our rated currents because we were already told what our rated voltages are. Okay. So we have a rated voltage of 44 kilovolts RMS on the high voltage side and a rated voltage of 220 volts RMS on the low voltage side. So my question to you guys is, which of these is the primary voltage and which of these is the secondary voltage? Perfect. Absolutely correct. So because we're told explicitly that this is a step down transformer, that means our primary voltage is the high voltage side and our secondary is the low voltage side. Okay. So our current I1 should just be 240 kilovolt amperes divided by V1 or 240 kilovolt amperes. Hold on. Sorry, I made just completely and utter boneheaded mistakes here that I need to fix that I just realized. So I apologize. This should be the magnitude of the voltage times the magnitude of the current, magnitude of the voltage times the magnitude of the current, magnitude of the voltage times the magnitude of the current in all but the original relationship. My apologies for not remembering that we're only dealing with magnitudes when we're calculating P, Q, and S magnitude like that. So sorry for the complete brain fart. So this is going to be 44 kilovolts RMS. Putting this into my calculator. All this old crap. 240 divided by 44. I get 60 over 11 or 5.455 amps RMS. Very similarly, I can say that my magnitude of my secondary current, I2, is 240 kilovolt amperes divided by 220 volts RMS. So 240 times 10 to the 3, I'm dealing with kilovolt amperes, divided by 220 gives me 1090.909 amps RMS or 1.091 kiloamps RMS. All righty, so that was the easy part. Now we've got to figure out what our reflected load impedance is. And what's interesting is that we don't know what our non-reflected load impedance is. So, anybody have any thoughts on how we might figure out our non-reflected load impedance? So we're told some pretty important pieces of information here, okay? So the first piece of information that we're told is that our transformer is fully loaded. And so if our transformer is fully loaded, that means that it is delivering rated voltage and rated current at our primary and our secondary, right? So we know the magnitude of the voltage V2, and we know the magnitude of the current I2. So what we've got to figure out is effectively what our phase angle is. Okay. So we scroll down here. The phase angle theta S is by definition the difference between the phase angle of the voltage and the phase angle of the current, which is literally the same thing as the phase angle of the impedance. So if we can figure out what theta S is, we will know what the phase angle of our impedance is. We already know what the voltage drop across our impedance is, magnitude. We know what the current flowing through our impedance is, magnitude. So we should have the magnitude of our impedance from those two quantities and the phase angle of our impedance from this quantity. And that lets us know what our impedance is. Okay. So this begs the question, how do we solve for the phase angle theta S and theta Z, because they're the same thing? We were told what power factor our load operates at. The power factor is what's related to that quantity, theta S, right? So we have power factor is equal to the cosine of theta S. That's how the power factor is literally defined. Then theta S is going to be equal to the inverse cosine of our power factor, which for us, that's going to be the inverse cosine of 0.9. If I wrote things down correctly, yes. So the inverse cosine of 0.9 is 25.842 degrees. Is this angle supposed to be negative or positive? Why is it positive? Because it's a lagging power factor. Wonderful job. Glad you guys remembered that. That's really legitimately fantastic. Not to be insulting, slightly surprised. Hopefully that wasn't too dickish, but yeah. All right. So this is theta Z. The magnitude of Z is just going to be the magnitude of V2 over the magnitude of I2, which we know is 220 volts RMS divided by 1090.909 amps RMS. So 220 divided by this guy gives me 0.2016 repeating ohms, and therefore our load impedance is 0.2016 repeating with an angle of positive 25.842 degrees ohms. Referred to the primary side, that's just going to be ZL over A squared. What's A again? It's our turns ratio, right? Were we given any number of turns or anything? We could do I2 over I1, or no, so I2 over I1 wouldn't be A. I1 over I2 is A, or V1 over V2 is A. Yes. So let's do, this will be ZL times the magnitude of V2 squared. No, I'm sorry, V1 squared. I'm messing myself up here now. Right. So just to be clear and making sure that I'm doing this correctly, I'm going to write it down over here. So A by definition is N2 over N1, which should be the magnitude of V2 over the magnitude of V1. Since I'm squaring that relationship, that's why I'm squaring things, and because I'm dividing by A, that's why I have a V2 in the denominator and the V1 in the numerator. Okay. So everything seems to be on the up and up now. So that's going to be 0.2016 with an angle of 25.842 degrees ohms times 44,000 volts RMS divided by 220 volts RMS. And I'm just going to square this thing. Okay. So $44,000 over 220 squared, I get to be 7.260 plus J 3.516 kiloohms in rectangular form. And 8.067 angle 25.842 degrees kiloohms in polar form, just depending on which way you guys have your calculators set up. All right. I think this is a good stopping point for today because I'm tired and I don't want to do it. Yes. So the relationship between RMS and the peak value is just RMS is peak value divided by square root of 6. So I don't know that we're ever going to deal with peak values in this class. I'm going to do everything with RMS value. For your exams and stuff like that, you're allowed to bring an equation. So you can put it on there if you want to, but everything that I'm going to be dealing with could be RMS. I can't think of a reason why it wouldn't. So. Any other questions? All right, so on Tuesday, we will introduce the practical transformer model. So effectively talk about what happens when we have all the various loss mechanisms like copper losses due to our windings, core losses, all of that kind of good stuff. Talk about the cantilever equivalent circuits, which is just a way for us to effectively simplify our equivalent circuit to be less annoying to use. I think we'll talk about voltage regulation and efficiency, and then we'll be done with this topic. That'll be everything on exam one, absolutely right. After the break. Yes, for sure after the break. Hmm? It, so let's talk about that here briefly. I am considering pushing your test back a day. And us having a review day slash me finishing things up just in case I don't get things finished up next Tuesday on our first day back. And so I personally would prefer if you did your homeworks before you took the test, because I think it will be of immense value for you to do your homeworks before you've taken your test. For those of you that had me before, I feel like you pretty strongly understand what I'm dropping there. So not doing the homework is a fantastic way to fail the bejesus out of the test. So I would like to have it structured in such a way that the homework is due as early as the day of the test to make you do it so that you don't, fail the test. Would anybody be terribly opposed to us having a review day when we get back and then pushing that test until the following Tuesday? Okay, so I'll be less of a dick then, and we'll do it. Yay. All right, thank you guys. See you on next Tuesday.